Hello, my name is Casey Ramos. Today we'll be calculating total energy of heating curve process and usage of the Clausius-Clapeyron equation. Question 2 asks us to explain or show the work for the following statements. The first being, when 65.8 grams of water at 37.5 degrees Celsius freezes to negative 13.8 degrees Celsius, it gives off 34.2 kilograms of heat. Basically, what is being asked by this problem is, given the values of the grams of water at an initial temp to its final temp, validate that 34.2 kilograms of heat is given off. To start, I am writing down the values given by the equation and drawing the heating curve for water with them, starting with 37.5 degrees Celsius, the initial temperature, and drawing a line down to 0 degrees Celsius to show change in temperature, then a horizontal line at 0 degrees Celsius to show phase change, and lastly, a line going down towards negative 13.8 degrees Celsius, which is our final temperature. I also wrote that Q total, or the amount of heat given off, was 34.2 kilojoules. The approach that will be taken to solve this problem is that I first solve for the amount of heat that is generated between the three changes that water goes through, and then adding them all up to get the total heat generated. The three equations I will use will be Q equals m times specific heat capacity of water times delta T, Q equals N times delta H, and Q equals m times specific heat capacity of ice times delta T. Step 1 is a temperature change going from 37.5 degrees Celsius to 0 degrees Celsius. With that, I decided to use the equation m times the specific capacity of water times delta T. I then plugged in 65.8 grams as our m, 4.18 joules per grams times degrees Celsius as our specific capacity of water, and for the change in temperature, we did 0 0.0 minus 37.5 degrees Celsius, which in the end gave me a Q1 of negative 10.314 kilojoules. Step 2 was a phase change, going from liquid to solid. So the equation that I decided to use was Q2 equals N times delta H. With that, I plugged in 65.8 grams of water, which is what we started, times 1 mole of H2O over 18.02 grams, then multiplied that by negative 6.02 kilojoules per mole, and with that, that gave me a Q2 of negative 21.982 kilojoules. Step 3 was a temperature change going from 0 0.0 degrees Celsius to negative 13.8 degrees Celsius. For that, I use the equation m times the specific heat capacity of ice times delta T. So I plugged in 65.8 grams times 2.09 joules per over grams times degrees Celsius multiplied by negative 13.8 degrees Celsius minus 0 0.0 degrees Celsius, which gave me a Q3 of negative 1.898 kilojoules. I then added up all three of the Qs, which gave me the Q total of negative 34.2 kilojoules, which is exothermic, which is our answer. Question 2, Part B, again asks us to explain. This time, propane has a normal boiling point of negative 42.05 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. At exactly 45 degrees Celsius, propane has a vapor pressure of 15.1 atm. Essentially, what is being asked by this problem is, given the values of boiling point and heat of vaporization for propane, validate that at 45 degrees Celsius, the vapor pressure of propane is 15.1 atm. As you can see, I am writing down the variables and values given in the problem to organize my thoughts. Pressure 1 is 760 torr, pressure 2 is 15.1 atm, temperature 1 is 231.1 Kelvin, temperature 2 is 318.15 Kelvin, and the heat of vaporization is 19.04 kilojoules per mole. The approach that will be taken to solve the problem is that I will take all the variables given in the equation, excluding P2, as that is what we are solving for, and plugging them into Clausius-Clapeyron's equation to get our answer. For my first step, I decided to use the two-point form of the Clausius-Clapeyron equation because we had two different points to use. With that, I wrote out the entire equation again and then plugged in each of my values, excluding P2 again, as that is what we are solving for. I then put into the calculator in parts, so I got ln P2 minus ln 760, which is equal to negative 2,290.113 K times negative 1.1840 times 10 to the negative third 1 over K. And with that, I then simplified it once more in the calculator, which gave me lnp2 minus 6.6333 equals 2.7115. Next step, in order to cancel out ln on the left side, I then did it to the e in my calculator. So e ln p2 equals e 9.3448, which give me a p2 of 11,439.11 torr. But because the equation was asking for the vapor pressure in ATM, I then converted that and I got 15.1 ATM. In both problems, what's being asked of me was to validate whether the values given equaled the final heat generated or vapor pressure that was given. My approach to solving them both was writing out what was given to me at first and then plugging those values into the equation the problems called for to get my answer. For both parts, the answer I obtained was that the data was correct and did equal what was given.